Okay, so let's conclude this chapter by looking at the last important feedback among the major feedbacks. Remember, we haven't done any vegetation feedback and others. So lapse rate feedback is basically related to how the vertical structure of the atmosphere itself changes with perturbation to radiative forcing, like the anthropogenic greenhouse gases. To remind ourselves, lapse rate is just the vertical rate of change of temperature, which is around 10 degrees centigrade per kilometer in the tropics, and is probably around 6 degrees centigrade per kilometer when you go to higher latitudes. And you can see that in this zonal mean meridional section of the temperature from MSEP reanalysis, which shows the height here and the latitude here, and equator is down here. We know the asymmetry for ITCZ and so on, so the warmest waters are to the north here, and you have also asymmetries in the hemispheres and so on and so forth. So this is the monthly long-term mean over a long enough period. The main point I want to make here is that you have the tropopause at about 12 kilometers in the tropics, and then it drops off as temperatures get colder and the atmosphere gets heavier and shrinks in the troposphere. So the tropopause drops off. And the other thing we want to note is that what we already mentioned in terms of the increase in temperatures as we go up into the stratosphere, which we cannot see here, but that's one of the consequences of global warming that we will close this chapter with. So what is the lapse rate feedback? Here is the schematic illustration of the changes in the vertical temperature structure in the tropics and in the mid-latitudes. So you expect the tropics to be less steep convection. Deep convection is mixing up the atmosphere, taking the heat into the upper atmosphere and warming the upper atmosphere with condensation, heating and other things. So you have different lapse rates. And then the mid-latitude, the horizontal flow limits the warming to the surface and the lower atmosphere, which causes lapse rate increase. So we are here talking about how lapse rate changes with global warming. So we are going from the unperturbed state to the perturbed state, where global warming increases surface temperatures, and deep convection would increase in the lower latitudes, which takes the heat to the upper levels. So the dashed line is the same as here. They are parallel, so they are parallel here as well. And the solid line here shows that the heat is moved from the surface to the upper level, so the upper level heats more, so now you are emitting more long wave radiation, sigma T to the fourth, in the upper levels, so you are losing more energy. So it's a negative feedback in the lower latitudes, whereas when you go to mid latitudes, you don't have strong vertical motions. Horizontal pressure gradients drive large part of the circulation, which is what we said here when we said that in the mid latitudes, reduced warming at the surface is enhanced because of the change in the adjustment in the pressure. So the upper atmosphere is warmed less than the lower atmosphere. Remember, greenhouse gas effect makes the surface warmer, and there is no way to move that heat up to the upper atmosphere in the mid latitudes. So the net feedback then would depend on not just lapse rate change in one latitude, but has to adjust the whole atmosphere globally. Overall, several climate models yield a lapse rate feedback of minus 0.84 plus minus 0.26 watts per meter square per Kelvin. So it's a net negative feedback, but has a significant uncertainty of almost 30%, which is less than cloud feedback uncertainty, but still pretty significant. So now, to summarize, let's put it all together. the total feedback and hence the sensitivity is to take the Planck feedback from the models at minus 0.32 and add all the feedbacks we looked at, water vapor, cloud, ice albedo, and lapse rate in this case, which adds up to 1.9 watts per meter square per Kelvin, and we end up with net feedback of minus 1.3 watts per meter square per Kelvin. We have to now translate this to equilibrium climate sensitivity, which is defined as temperature change for doubling the CO2, which we represented as delta T2x. So that is minus 1 over lambda, the climate sensitivity we derived here, times delta Q 2x, which is the change in radiative forcing resulting from doubling the CO2. So the doubling CO2, let's look at that first then. The radiative forcing associated with the changes in the atmospheric concentration of CO2 from this paper gives us delta Q CO2 as 5.35 watts per meter squared times natural log of the CO2 concentration divided by 280 ppm. So we are basically doubling from the pre-industrial level of 280 ppm to 560. So in that case, delta Q2x is 5.35 watts per meter squared times 560 divided by 280, which gives us 3.7 watts per meter squared, which is a well constrained number in terms of just the physics of it. So delta T2x in that case is minus 1 over lambda delta Q2x gives us 2.85 Kelvin, which is the estimate we can do with this simple approach. But here you look at the overview of most of the important feedbacks in the atmosphere: water vapor, cloud feedback, albedo feedback, which I didn't mention before, lapse rate feedback, and all together. Thanks to the latest remote sensing and radiosonde measurements, which are the vertical profilers, the sum of water vapor plus lapse rate can be estimated more precisely than the single components because they are closely tied together. You end up combining them and getting a better estimate of the two together. Total feedback is clearly positive. So the net feedback of the climate system right now is positive. Vertical bars indicate the uncertainty in the circulations of Soden and Held. This figure is again from Sandrine Boney's work. So feedback strength in watts per meter square per Kelvin from different estimates. These are radiative convective models, which is the kind of energy balance we looked at. Soden Held estimate from models and estimate uncertainty. So they have also a calculation where they fixed the relative humidity, and another paper by Winton. I won't go into the details of the differences, but fixed relative humidity, why is it important? As you warm the temperature, not only does the air hold more water vapor, but the saturation vapor pressure also increases with temperature. So relative humidity is critical to see if the change of saturation humidity and specific humidity is such that relative humidity remains almost constant, which turns out to be the case over the oceans, but obviously over land you don't have a constant supply of water vapor, so that can change with global warming over land. So water vapor feedback, you can see the different estimates and the ranges. For cloud feedback, again, can be negative in some cases by Coleman and can be large positive numbers. Albedo feedback, again, positive but a significant range. Lapse rate feedback, very large negative numbers to slightly positive numbers here. Water vapor plus lapse rate feedbacks, positive with the range, and all of them together have net positive but quite a range. So this is what we talked about before in terms of estimating equilibrium climate sensitivity. So here is a figure showing mean of 21 atmosphere ocean GCM models which were used for the projection of climate change for the fourth assessment report of the Intergovernmental Panel on Climate Change. The zonal average temperature change in the atmosphere over the last 20 years of the 21st century for the emission scenario A1 21st century, for the A1B scenario, which is the scenarios used in AR4. AR5, they were called representative concentration pathways and focused on the radiative forcing resulting, and in AR6 they are called shared socioeconomic pathways, which combine sustainability scenarios with the radiative forcing scenarios. The troposphere shows a warming, as we expect, amplified between 7 and 12 kilometers in the tropics because surface heat is being convected up and heating the upper atmosphere more, as well as on the surface near north of 60 north. So we get polar amplification, especially in the northern hemisphere. The stratosphere shows a cooling, and there is a good reason why the stratosphere cools. To first order, you can think that as the greenhouse effect because of CO2 warms the surface, the outgoing long wave has to increase to keep up with the warming, and the question then is where the warming comes from. If we remember our lapse rate, the temperatures cool and the atmosphere is mostly emitting from the upper levels, and the upper levels have reducing density as well. So the emission of long wave to space begins to occur at higher and higher altitude. So the radiating layers are basically occupying larger part of the upper atmosphere. Net, the energy coming into the stratosphere is reduced. Because most of the energy is being trapped by CO2. Some of that energy is not available for warming the stratosphere. So you can read up nice articles on this under Skeptical Science, Real Climate, and other websites which offer such explanations for lay people. But just remember that we expect the tropospheric warming to result in stratospheric cooling, but there are many details there as well. And this shows the evidence for that. This is modified from an IPCC figure by a Harvard prof, and I just stole it from his website. Global anomaly relative to 1979 to 1990, so lower stratosphere from the sounding unit from UK Met Office estimates, and this is another product here, balloons. This is from the balloons, and this is the some other product. You can look it up. Okay, so basically volcanoes perturb the stratospheric temperature, but the trend is clear that there is a cooling happening in the stratosphere, which is consistent with the physics and the fact that models are doing it properly. So this is now finally the probability distribution from studies determining the climate sensitivity based on past climate changes. So sensitivity doesn't need to be constant through the long geologic timescales, because albedo, all of the feedbacks we talked about are different as well, right? So as so that's A. You can see constrained by past transient temperature evolutions, there are various estimates here, and these are the climate sensitivities, and this is the probability distribution of the frequency of climate sensitivities, and you can see there is a large range in both cases. This is constrained by climatology, so again multiple estimates, large range here. Unweighted distribution, this is B is same as in A, but 5 to 95% ranges and most probable values, so it's been reduced into percentiles where you have the most confidence, for example. C and D as in A and B, but based on climatology. E and F, unweighted or adjusted distribution of different models or of a model with different parameters. So models themselves can have sensitivities to the parameter choices, what we called as tuning early on. So the story remains the same, that climate sensitivity is a very hairy problem. This is the equilibrium climate sensitivity from CMIP6 models, and you can see the range is again quite high, from as high as 5.6 down to 1.9 or less. So this is the end of the second chapter, which has lots of information. Crux of the modeling and the issues were kind of touched upon here, but there are many more that remain that we will look at as we go into chapters further down. Okay.